Yeah, thanks a lot to the organizers for the invitation. And since this is not the last talk of this program, but the last talk of this workshop week, we should also take the opportunity to thank the organizers for putting this together. So what I will speak about is on joint work with Adrien Brochet and Lukas Müller. And yeah, it is going to be about modular functors mainly, and then also a little bit factorization, homology, and how it helps in constructing modular functors. So I should probably start by explaining very roughly what a modular functor is, and I will give an informal definition first. So informally, a modular functor is an assignment that takes a surface like this one, possibly with boundary. And when I say surface, for me this is always compact and oriented. I would not say that all the time, so I would just say surface, and there will be boundary labels. And for the moment, let's maybe just think of these boundary labels as some elements from some sort of label set that I have in mind. Thinking about this as a set will later on not be such a smart thing, but for the moment, let's do that. And yeah, so what does this assignment actually assign? It assigns a vector space. And it's going to depend on the surface and on these labels that I have specified. Yeah, and then of course this is done for all surfaces, for all labels, and this is not just a vector space, but this comes with an action of the mapping class group of that surface. And the mapping class group, just to remind you, this is the following thing. So you take the surface, you take the diffeomorphisms, and when I say diffeomorphisms, it is going to be implicit that they will preserve the boundary, or I mean more precisely, I should actually choose here boundary parametrizations. They will preserve the boundary parametrizations. They will also preserve the orientation. And then, yeah, I take the diffeomorphisms from the surface to the surface, and I take pi 0 of this topological group, and this is what people call the mapping class group. And as an example, so the mapping class group of the two torus is famously SL2Z. Yeah, so this is the kind of just to give you an impression of what kind of groups to expect here. Yeah, in genus 0 you get the braid groups, and this is typically in the case that we will look at, this will be finite dimensional, this vector space. And there's also there are more things, so I will just write plus here. So there is also an operation of orientation reversal for the labels. So we would like to have a notion of ingoing versus outgoing labels. We will later on realize this in a slightly different way, so this is also why I will not talk about it too much. And then there is going to be a compatibility with gluing. Yes, that would be fine. Yeah. There's a slightly, so there's a slightly different way to think about this. So the origin of this is conformal field theory, and there this thing would be called a conformal block. Conformal block of that surface. And then, so why do we have vector spaces and mapping class group representations on them? This is because in conformal field theory, sometimes what you want to have is a projectively flat vector bundle on the moduli space of Riemann surfaces. And what is the flat vector bundle? You will then have maps from pi 1 of that space to, you will represent pi 1 of this space and pi 1 of the moduli space of Riemann surfaces. Those are exactly the mapping class groups, and this is why you define it like this from the start, but this is where this comes from. So if you want to think about vector bundles on the moduli space of surfaces, then you can equivalently do that. But I would write it like this. And then, so the notion, so just to indicate also who came up with this, this has evolved over time, needless to say, but so this started with work of Siegel, Toraev, Bakalov, Kirillov, and Ulrike Tillmann, and many more. And there are different versions of all of this. And again, this is slightly informal, so I will later on say how you would actually properly define this so that you don't have to hand wave too much about this compatibility with the gluing and so on. So.
About connected components, are you also asking for some compatibility that if you have several connected components, it's the tensor product of the vector space?
This is something that when you phrase the compatibility with gluing correctly, then it would fall out of that as well. But this will be the case, that the Dishon union of surfaces is going to be sent to the monoidal product of the vector spaces. So why do you look at this? So the first reason is the study of mapping class groups. Mapping class groups are interesting groups, and getting meaningful finite dimensional representations for them is actually very non-trivial. And if you have constructions that do that, that is relatively interesting. In particular, there's the question whether mapping class groups have finite dimensional faithful representations. It's the question of linearity of mapping class groups, and a lot of the partial progress in this direction, most prominently the so-called asymptotic faithfulness of mapping class groups. This is something that has been done using the theory of modular functors. This is the result of Jörn Ellegard Andersen. He proved this asymptotic faithfulness of mapping class groups. Then this is related to topological field theory. So if you have a three-dimensional topological field theory, a once extended one that we have seen in two talks actually already, then you can restrict that to surfaces. So you are forgetting about the non-invertible three-dimensional Bordisms, and then what you will end up with is exactly such a modular functor. But modular functors will exist in situations where you cannot build a TFT, so it's more flexible. And also if you don't care about, say, the invariance for closed three manifolds, then why construct them? Because typically this is difficult. And then, so I mentioned that this comes from conformal field theory. And it's not only motivated by this, but you can actually do computations in conformal field theory using that. So there is this TFT construction of correlators due to Fuchs, Runkel, and Schweigert from the early mid-2000s. And what they did is that they started with some sort of something that describes this conformal field theory, a vertex operator algebra. They built such a modular functor, in this case actually even the 3D TFT, because they were looking at rational conformal field theories. And then they showed the existence, or also constructed something that is called correlators. This is, so this is something that you can do with this. And then another thing that I want to mention here is the homological algebra of non-semi-simple representation categories. And the idea is here that you can come up with homotopy coherent differential graded analogs of this, where you assign chain complexes to surfaces. And then you can build such things from non-semi-simple representation categories, and this gives you a topological access to quantities like the Hochschild homology or the Ext algebra of these non-semi-simple representation categories. And this is something that was done by Lendner, Mirach, Schweigert, Sommerhäuser, and also myself. So this is something that is a much more recent, and so it's a derived analog of this. In order to say something about the classical constructions of modular functors, we need some terminology. We have, I think, heard some of it, but not all of it. So so there will be the notion of a finite linear category, and this is going to be a linear category that is linearly equivalent to A mod, and this A here is a finite dimensional algebra, and this kind of mod here, those are finite dimensional modules. There's a more intelligent description of finite linear categories in this, but this one is shorter. And then if you have this, then there's the notion of a finite tensor category. This was defined by Etinghoff and Ostrich. And this is a finite category with a rigid monoidal product. So let's give a name to this, A. And this monoidal product, it's defined on the linear product of linear categories. It's rigid, so it has both duals, so it will be exact anyway, so I can write it like this. It's going to descend to the linear product anyway. Rigid monoidal product and a simple unit. This is not super relevant, but it's in the original definition. And if this is semi-simple, then people call this a fusion category. So then there's more structure that this can have. And this is a braiding. These are isomorphisms of this form. So isomorphisms that make X tensor Y isomorphic to Y tensor X, and then there are some coherence conditions on this, so-called hexagon axioms. And there is also something that is called a balancing. Those are natural automorphisms, the natural automorphism of the identity, in fact, such that the component at the monoidal unit I is just the identity. And, yeah, okay, that's not going to fit. And the condition that this balancing at a monoidal product is the monoidal product of the balancings up to a double braiding. And this is a so-called ribbon structure. If we have additionally that the balancing at the dual object is the dual balancing. And then we call this a ribbon category. And finally, we call the braiding non-degenerate if we have the following. So if we have an object that trivially double braids with all other objects, then this implies that it is just the monoidal unit or a finite direct sum thereof. Yeah, so the class of objects that trivially double braids with all of the others is as small as it can possibly be. And then, yeah, first real definition would be that the one of a modular category. And yeah, a modular category is a finite ribbon category with non-degenerate braiding. How do you get modular categories? So the sources are, for instance, certain Hopf algebras. So you take such a suitable Hopf algebra, you take modules over this, and then if this is a nice Hopf algebra, for instance, the quantum double of a finite group, then this is going to be such a modular category. And another source are vertex operator algebras. So this is something that for me is a little bit of a black box, but if you have something that is called a vertex algebra, so some formalization of a two-dimensional conformal field theory, you can also take modules over this VOA in a certain way, and you will end up in nice situations also with a modular category. And then, so the classical construction basically says that if you have such a modular category, then as the name suggests, you get a modular functor. But this is actually, even though it sounds a little bit tautological, I mean, if you look at the definition, it's absolutely not clear how this goes, and this construction is actually relatively complicated. So theorem, and this is this is part of the Richtig-Interal construction, if you wish, at least in the semi-simple situation, and in the non-semi-simple situation, this is a result by Lubashenko. So this is from the 90s. Yeah. And yeah, let's summarize this. So the result is basically modular categories produce modular functors. But how does this work? So if we have a surface like this, so it has genus G, and it has n boundary labels. So the labels, they are in a modular category A. Yeah, so this is the thing that we give ourselves to construct the modular functor. And then what this assigns is the following. So it will assign a Hom space. So I will write the Hom space like this, the Hom space in the category. And it's going to be a Hom from the monoidal unit. And then I take these objects that I had here, and then I tensor this with an object F, or rather the G's tensor power of it. And this object F is the so-called canonical coend over the category. So this is again an object in the category that is defined as a certain co-limit. In the semi-simple situation, this F is really just the direct sum over the simple objects tensored with their duals. And if it's not semi-simple, then it's not so easy, but it is, morally speaking, still relatively close to it. But there you actually cannot just have this direct sum. You really need this different prescription. And to some extent, yeah, I mean, this is somehow invented to actually have this generalization. These mapping class group representations that that you get from this, they are relatively, they are extremely non-trivial. I didn't even tell you how this thing acts, but I mean, if you are in genus 0, then you don't have this, so you just have these objects, so you're going to use the braiding to get the mapping class group representations. That's very reasonable, because genus 0 mapping class groups, they are the braid groups, yeah, or framed braid groups. And then, yeah, in higher genus, it's tricky. I mean, even for the torus already, there you will see this thing showing up, and it's saying what it does is, well, it's something that these people have figured out, but it is not very easy.
What's your sign to Dane twist?
Well, the Dane twist, it's going to be this balancing. Yeah. Yeah. So in the semi-simple situation, it is relatively transparent where this construction comes from, because if I have a semi-simple modular category, then there's a result by Bartlett, Douglas, Jean-Mapris, and Vickery. They prove that semi-simple modular categories, that they're equivalent to once extended three-dimensional topological field theories. And so for this modular category, if it's semi-simple, you get this once extended 3D TFT, you restrict it to surfaces, and this is the thing. This is why I put here Restick into Reif, because it is a part of the Restick into Reif construction. If the category is not semi-simple, then this is a lot less clear why you would even do this. It's good that it works, but maybe a little less clear why, actually. So what we are trying to do is to actually describe all modular functors that you can have, and yeah, to somehow classify them. Because also, I mean, here you get that modular categories, they produce modular functors, but would the modular functors also produce modular categories if you somehow reverse this? And what we find is actually that this is not true. And yeah, so how would one do this how would one approach this? So what you can do is that you pretend you already have your modular functor, and then you try to deduce step by step what kind of structure you actually get if you evaluate it on surfaces. That's not even that, at least in genus 0, it's not even that hard. So, yeah. So the first observation is that the labels for a modular functor form a linear category A by evaluation on the cylinder. So that is good, because that means that if we have such a modular functor, then we have already such a category, and by the notation I already suggest that, yeah, there's a relation to this one, and this is in fact going to be true. But at the moment this is just a linear category, there's not more structure on it. But yeah, any surface it gives us a functor from A to the N to vect. And I choose here all of the boundaries as incoming. I will need to have some mechanism later on to actually turn the incoming ones into the outgoing ones, so this is going to have a cyclic structure. And in fact, this is going to be formalized so the way that we formalize this is using cyclic algebras over cyclic operators. This is something that I will suppress here a little bit. This is also why I gave the informal definition. If you really wanted to make this precise, then you need all this, yeah, all these operats, and yeah, but this is maybe for today not super critical. I will make here the for this talk, I will say that this A is actually a finite linear category, and that this functor is left exact. Those are conditions that are not actually not really relevant, but they will allow me later to link this better to other known constructions. Yeah. So what structure do we get on A? So we have this surface, the pair of pens, and now I draw this with one outgoing boundary, just so that it's, yeah, you can think of this really as a product. This is going to be sent to a functor like this, if I move one of the A's to this side. So this is a monoidal product. I think this is not very hard to believe. There's a unit, that's this one. So monoidal product. There's a unit here, and there's a braiding. This is because there's a mapping class that switches these two legs. Yeah. So this is why this this A is a braided monoidal category. And then if I have the cylinder, then I have the Dehn twist around the waist of the cylinder, and this is going to give me a balancing. And this whole thing, of course, this is known. This is just a presentation in terms of generators and relation of the operat of genus 0 surfaces, aka the framed E2 operat. This is a result by Salvatore and Wahl.
Why does the cylinder not give the identity?
It gives the identity as a functor, but the Dehn twist will give you an automorphism of the identity functor. It's on a different categorical level, yeah. Yeah. Sorry?
You just missed your second statement.
So the surfaces, they give you functors, and then the mapping classes, they give you natural isomorphisms between the functors. This is why this thing here and this one, they give you functors, but the Dehn twist here gives you an isomorphism, even though the cylinder, and this was Alex's question, the cylinder is sent to the identity functor. But the Dehn twist is an automorphism of the cylinder, so that you get an automorphism of the identity functor. Yeah.
Which of these results really depends on the assumption that it's linear, for example? I mean, okay,
So far, none of it. Absolutely nothing. Yeah. The operatic algebras, they can take value in any kind of symmetric monoidal bicategory, and then it's fine. Yeah?
So, here, when you define a formally modular functor, you used to say compatibility with some class compatibility.
Yeah.
Precisely, the compatibilities, the minimal set this.
Sorry, I'm not so sure whether I understood that. Sorry.
Because here you start with a modular functor.
Yeah.
But you do not give the definition.
Yeah, so I didn't say really what the compatibility with the gluing means. So if you really want to define this, so what you need to do is you take the modular operat of surfaces, modular operat in the sense of Getzler and Kapranov. This is somehow the thing that I don't want to define here because it's very tricky. And then you look at modular algebras over the modular surface operat in some symmetric monoidal bicategory of linear categories. And then you will find that somehow the operatic composition will translate into the composition in the endomorphism operat of your category. And this happens to be Lubashenko's left exact coend. But this is actually something that you have to show. So if you want to take these conformal blocks, and maybe you, for those of you who have seen it, so there's in this paper of Lubashenko, also in the follow-up papers by Fuchs and Schweigert, these left exact coends, these relatively weird coends that make sure that you don't run out of the category of left exact functors. And this is exactly going to be the composition. But this is something that actually you have to show, but it glues via coends. Yeah. Yes. So yeah, I should leave that. How am I doing time-wise? Okay, yeah. So what we did with Lukas Müller is that we asked ourselves whether this is already everything that you get in genus 0. And it's not quite everything. So because there is, I mean, if you want to classify vector space value 2D TFTs, then even in that situation, it wouldn't be everything, right? Because there's also this surface that does, and that's also a cylinder, but somehow gives you a pairing. And this is also why 2D TFTs, they're not commutative algebras, but that they're commutative Frobenius algebras. So it's missing, all of this is somehow missing this Frobenius part. And this is a slightly tricky thing that you need to add in order to really have a full description of the genus 0 modular functors. And the statement is the following. So in order to complete the above structure to a genus 0 modular functor, one needs exactly a cyclic framed E2 structure on this category. And I would say what that means. This amounts exactly to an equivalence from A to A op making the Hom functor, this Hom functor from some object K, and so the object K, this will be the image of the monoidal unit under this D. This Hom functor, this is supposed to become representable. And just to remind you what that means, the representability means that we can write this functor again as a Hom functor. Like this. Yeah, and this equivalence is supposed to be the thing that affords this. Yeah, so in order to make this one representable, we use this functor D.
FE2 is framed E2.
Framed E2, yes. Yes, I should have. So framed E2, since I didn't introduce this, framed E2, you can also read this as genus 0 surfaces. Yeah, sorry. And then there's one more thing. D is going to be compatible with the balancing. Yeah, so when you build modular functors or TFTs from certain these categories, then whatever you're going to start with, it's always rigid, typically. Yeah, people don't look at, I mean, for most people, tensor category, as opposed to just monoidal category, means in particular that it's rigid. So if you see that there is now this anti-equivalence of A, then maybe the guess would be that, well, that's the rigidity. This is why actually the rigidity is somehow being enforced topologically. But that is not true. So this D is not going to be a rigid duality in general. It can be, but it doesn't have to be. And so instead of being a rigid duality, this is, where did I put this? This is something else. This is a so-called Grothendieck-Verdier duality. It's a weaker form of duality. So this whole thing where I've spelled this out, yeah, this thing, this D, and then the representability, but also this final condition here. So this whole thing is called a ribbon Grothendieck-Verdier duality. And this was defined by Boyashenko and Lindfeld in 2013. But there's the older notion of a star autonomous category, which basically does the same thing. This comes from information theory, where this D is supposed to be some sort of logical negation. Yeah. But of course, for us, that's not relevant. We just accidentally find this thing that then in other contexts shows up, which is good because this gives us examples. So.
Because I'm a bit puzzled. So this seems to be like comparing it with normal internal homes. It seems to be the wrong way around.
Yeah. Okay. Yes, it is. So this is also not. This convention is not the one that Boyashenko and Drindfeld use. This is the one that we use because we decided here to work with left exact functors. If you had chosen the right exact ones, then you would get the other convention. And we just choose the left exact ones because Lubashenko, for some reason, always works with left exact functors, and we have to make a choice. It's a bit unfortunate. Yeah. You can do it in any symmetric monoidal Y category. So whether you work with you can also drop the exactness requirement on the functors altogether, but then it doesn't make the theory more general. In fact, Ulrike Tillmann has shown that in this case you actually enforce things like semi-simplicity that you don't want to have. So it's, yeah. No, what she looked at is linear categories with the naive tensor product, and then you get things that you can do it, but it looks a bit weird. Yeah.
And the D has no compatibility condition with the monoidal structure or anything?
It does not. No, it's so one thing that, for instance, you don't have is that the dual of a monoidal product is the opposite product of the duals. You don't have it. That is something that you don't have. In fact, if you apply the dual to the product of something, you map the monoidal product to a different monoidal product. So an equivalent way of thinking about this is a monoidal category, a category with two monoidal products that are interchanged by this D. Yeah. So So one thing that this is good for is that, so this is another theorem. This is also with Lukas Müller, is that if you have this genus zero modular functor, then you could ask, well, does it extend to all surfaces? And it doesn't. But it will extend to a modular operand where we basically do the same thing as we did for the modular functors, where we had these surfaces, but we have three-dimensional handle bodies instead. So there are as many three-dimensional handle bodies as there are surfaces. They're also just characterized by the genus and the number of boundary components, but the mapping class groups that they have, they are different. For the handle bodies, they're smaller. They are just subgroups. But still, it is helpful that this already extends to the to all handle bodies. So this uniquely extends to all handle bodies. And how does it extend? So if we have such a handle body, it looks on the blackboard, it looks like a surface, but now this is filled. Yeah, this is the difference. Then you can show that this unique extension will actually send this to the following Hom space. So we will have here this object K, and then you get this with F being the following thing. So you will take this coend in the delinear product and you apply to the entire thing the monoidal product. Typically, in the case of modular categories, you just put this pass the coan and you put it here, but since now we don't really know whether the monoidal product is exact, we can actually not do it. So if you, in this case, actually you would wonder whether the correct thing would put the tensor product here, or first does the coan and then the monoidal product, and the answer here is that this is the correct thing. Yeah, so the unique extension is this one. And so this is relatively nice to see, because if you have a modular functor, then you can always restrict it back to the handle bodies, because handle bodies, they map to surfaces, so you can restrict along this map. And then this statement tells you that whatever kind of vector spaces with mapping class group representations you can possibly assign, they are always this. So if you ever wondered why do you have to write down this home space with this coan, then the answer is that you have no choice. They are all of this form. So this is now not anymore this. So I mean, for instance, for me in this Lubashenko construction, this vector space is, of course, it's very well motivated, but I would still consider this some sort of ansatz that works. This one tells you that you actually cannot do anything else. It's not possible. You can just do this one. And the K is this K, this D of I. And it's also called, the Boyaschenko-Drinfeld calls it the dualizing object. Yeah, so since this structure where you have, instead of the surfaces, the three-dimensional handle bodies, since this shows up several times, we decided to give a name to this. So we call this an ansular functor. Because, so yeah, that sounds similar to modular functor, but so ansa in Latin means handle, so we thought that we can call this an ansular functor. So, so far what we have seen in this language would be that ansular functors, that they are equivalent to ribbon Grothendieck-Verdier categories. And now, extends as a modular algebra. So this is a no, it's kind of. So there's an extension for cyclic and modular operas. It's similar to a Kahn extension, but it's called the modular envelope, and that is the one that you need to use. Yeah, so for every thing that is here already consistently defined in genus 0, you can extend it to handle bodies. And note that in genus 0, whether you look at handle bodies or surfaces, it doesn't matter. Yeah, the mapping class groups as genus 0 handle bodies are the same as genus 0 surfaces. They're just the frame break groups. I should have possibly said that. Yeah, it's yeah. Exactly. So then I hope that I can still explain how you extend this, or how you look at the extensions to surfaces using factorization homology. So first of all, we proved that that the space of extensions from genus 0 of extensions of a modular functor of a genus 0 modular functor to higher genus this thing is contractible if it's not empty. And this is a result that for modular fusion categories appears, for instance, I mean, without, of course, considering a space of extensions, but in a different form. This appears in work of Anderson and Weno. Which means that the extension at this point is not structure, it's a property. So it works, or it doesn't, but if it does, then there's no choice. Which is, of course, good, because now we can ask what the property is that we need to get the extension. And for this, we need factorization homology. So we need factorization homology. So what does factorization homology do? So in our case, it will take this A, this thing that in particular is by now, since it is defined already in genus 0, a braided monoidal category, and we can integrate this over a surface. So this is a surface, and this thing is at least braided. And so this factorization homology, this was invented, or at least a precursor of this, by Beilinson and Drinfeld. It was then developed by Lurie and Ayala Francis and many others. And what this basically does, and this is this is not really a full definition, but it is going to take n tensor copies of this coefficient thing that you want to put in, and it will do that for all embeddings of n many disks into the surface, and n is 0 or more, and then you divide out, but you divide out in a soft sense, in the sense of a homotopy quotient, relations whenever some disks that you put in are already contained in a bigger disk. Then you can somehow implement simplifications in this quotient. And so if A is also Grothendieck-Verdier, we can define for each handle body H with boundary sigma a map from the factorization homology of that surface to A to the n, and n is the number of boundary components. And you call this phi A of H. Okay, so this is something that you can define, and here you use the ancillar functor to do it. It's of course not obvious how you can do this, but I'm saying that you can define this. And now if you have this, then this allows you to write down the condition that you need to extend this. So and now we call A connected if all of these maps are isomorphic for different handle bodies with boundary sigma. And this is for all surfaces. Yeah, so this is something that I can just introduce here. I didn't quite say isomorphic as what, so this is a functor. They're not just not supposed to be isomorphic just as functors. There's actually the factorization homology for the annulus acts on this one and also on this one. This becomes a module map. It has to be an isomorphism of module maps. So I allow myself to not expand on that, but you have to, it has to be the correct notion of isomorphism here. It is, yeah, so if you know what a skein module of a handle body is, then it is basically a generalization of that. So it's, I mean, factorization homology is supposed to be some sort of generalization of skein theory, and yeah, this is somehow what this does. I mean, okay. I mean, it's not quite a cylinder over sigma, it's really this handle body over sigma. So if this is a finite ribbon category, then conjecturally there comes a certain 3D TFT attached to this. This doesn't only rely on the cobordism hypothesis, also on certain fixed point structures that this thing has, but this is something that in work of Jordan, Brochet, and Snyder shows up. If you actually had that TFT, then this thing would be a part of that TFT. Yeah, but you don't have, so we, yeah. We don't need this here. Okay, and then, so the main theorem, so good that I still managed to do that. So then the modular functors, they are equivalent to connected yeah, in the case when we work in Lex, ribbon, Grothendieck, Verdier categories. And then let me say say some more things. So now I have introduced the condition where you could have serious doubts that one can somehow check this or understand this. So modular categories are an example. In particular, I mean, actually, if the category is something that is called co-factorizable, which is dual to the factorizable that Ettinghoff and collaborators use, but so the co-factorizable is something that Jordan and Brochet and Snyder and Safronov use. If the category has that, then this implies this, and then you get a modular functor. Modular categories, even if they are not semi-simple, are an example of this, and so it would have to coincide with Lubashenko's construction because we have the uniqueness statement. But there are examples of modular functors that do not come from modular categories. I just want to mention this for the people who have heard this. So an example would be the so-called Feigin-Fuchs boson. This is a ribbon Grothendieck Verdier category that Allen, Lentner, Schweigert, and Wood have built, and this also checks the boxes, but it's not a modular category. And there's also the Drinfeld center of a non-spherical pivotal finite tensor category. So the experts will know that if you take a finite tensor category and take its Drinfeld center, it is always factorizable. But the thing is that even if it's pivotal before, it will not need to be ribbon afterwards. This is a slightly subtle point, but it will still produce a modular functor for this. And then regarding the ancillar functors, there are also examples of ribbon Grothendieck Verdier categories coming from VOAs, and they produce at least an ancillar functor. We don't know whether they produce a modular functor, but those examples would be interesting because they include monoidal categories whose monoidal product is not exact. Yeah, so if you have a VOA and you build these categories, and it can happen that the monoidal product is not exact, and the rigid categories that you usually have, they will never capture this because rigidity implies the exactness of the monoidal product. And somehow the idea is to get around this. And then, yeah, I should stop here. Thanks.
Thank you very much for this beautiful talk. Are there questions, or rather, more questions, comments?
Lukashenko's case, this F covalent has a lot of structure, so it's a hot algebra in the center. What happens in the cognitive case? Can you maybe read off connectedness from this object or something?
That's bless you. This is so this is a really good question. So I don't know whether it has all this structure. I don't think so. So the thing is, so when you say the Lubashenko coend, then probably you mean this coend, right? So the one that really lies in the category itself. So it has a central, so that is exactly the point. So it's actually better to regard this as an object in the center, and then it's a braided commutative algebra in the center, maybe even more things. And so I here you don't directly you would not directly get this, but I think the reason for this is just that the notion of the center for the if you somehow have things that are not finite tensor categories, and I think it's not this is probably not the correct one, and I think this is why you don't see it. Also, if you have a modular category, then the center happens to be equivalent to this one, and if this is not a modular category, then I think you won't have it. And then the question is, what is the correct one? Should I look at things in the center, or should I really maybe look at this one? And I think this is the one that actually has the more fundamental meaning, and this maybe. But I don't know, because if I look at this directly in the directly here in this category, I don't think I don't even see the algebra structure. This is the problem with this is that if you have the Grothendieck-Verdier duality, then if you have if you apply the duality to objects, then you would like to see this, but you don't have it. And then if you don't have this, then already this central monad doesn't make any sense anymore. Maybe if you somehow replace one of the, in the central monad you multiply from the left and from the right with the same monoidal product. Maybe you can fix it if you choose a different monoidal product that is conjugated with the duality. But that's just a guess. For the finite tensor categories, it's all the same, and you don't see it. So yeah.
I was hoping that if it's connected, then this is simplified. But I don't know that.
What I cannot do is to characterize this in terms of maybe this sort of Hopf pairing or so on the F. But I think, Brochet and Jordan, they have this characterization of invertibility, right? Which is, the invertibility will imply this connectedness, and there they have these different, they have all these things that are equivalent factorizable, co-factorizable, and then also this list of things that Shimizu has, and I think they already explain that even if you drop, they already explain that I think these things stop being equivalent if you if it's not applied to finite tensor categories, because one of the proofs that Shimizu uses something with Frobenius-Perron dimensions, and I would have no idea how to, I wouldn't even know what that means here. Yeah, Alex.
That you use factorization homology here, was that just as a tool in order to prove
Yeah, yeah.
There's something interesting about factorization homology here as well. Because your input A has a specific structure, so it has way more structure than
Yeah. No, it's a tool. It's a tool. This is also why I didn't say so much about it, because one thing that actually comes out, at least in the case of a modular category, is that this if I take the factorization homology and I take any handle body here and I look at this map, then this thing so if A is modular, for instance, this will be an equivalence. So this is actually, from the factorization homology viewpoint, this is maximally disappointing, because it tells you that the factorization homology here just counts the number of boundary components. But the thing is that this is exactly what you need to get the mapping class group representations, because the mapping class group representations are not on the factorization homology. We don't want to act on these categories. We want to act on the vector spaces. And somehow the moral of the story is that the more trivial somehow this thing plus its mapping class group representation on this category is, the more interesting the one on the vector space inside this gets, because it means that, in particular, it means that if you have a closed surface, this factorization homology is literally just vect. It's this is orthogonal. Yeah. So we're not looking for mapping class group representations on these categories. They're actually supposed to be as trivial as possible.
So this multi-channel pairing in a certain way makes this factorization homology quite trivial or almost.
It's not it's the non-degenerate braiding, not the non-degenerate pairing. The non-degenerate braiding makes the factorization homology trivial. I mean, the idea somehow is that if you have a modular category, then so Brochet, Jordan, Safonov, and Snyder, they showed it's a invertible object in this Morita 4 category of E2 algebras. So if you use the cobordism hypothesis, you get an invertible 4-dimensional TFT, and then if also everything with the orientation works out, you would get this 4D TFT, which in the top layers is so trivial that somehow the thing that is left is just a 3-dimensional TFT, which is then probably some sort of generalization of Reshetikhin to Raif, plus this modular functor. Again, none of this is really, this is all a little bit shaky for various reasons. Not only the cobordism hypothesis, it's also the fixed point structure that is missing. But at least for the modular categories, this would somehow be the explanation. And this here is this thing that you see here is basically this invertibility in top dimension. Yeah. But yeah, this is not, this is, yeah, I mean, this is the way that one probably should think about this. Yeah, that it actually comes from 4D. But in 4 dimension, it's so trivial that the only thing that you still see is this framing anomaly part. Yeah.
Can one also use this in some way to better relate and understand handle body groups representations? Like I mean, of course, if you have a mapping class group representation, then you would get one from the handle body group.
Yeah.
The converse, not necessarily.
Yeah, and no, the converse is somehow not true. I mean, one thing that you can use to understand these representations better is that, for instance, if you're just asking about a Dehn twist in the mapping class group of a surface, then you can always arrange this to be the Dehn twist also of some handle body. So you can use that to compute, for instance, the order of the Dehn twist. This sounds relatively easy, but it's actually not. And this is also something that we will do. So we will give criteria when the Dehn twists in these representations, they have infinite order. And so because if you have a modular fusion category, the Dehn twists, they always have finite order. So with regards to faithfulness, this is a little bit disappointing, but there are these Runkel, De Renzi, Gajnutinov, and collaborators, they have this quantum S2 example of this Lukashenko type modular functor where they prove it has infinite order, and we want to somehow, we want to give simple criteria when this happens, and for this relation between the handle-body groups of the handle-body groups and the mapping class groups is definitely useful, because for the Dehn twists you can always arrange this to be in some handle-body.
But I guess the relations will be quite hard.
Yeah, the relations, they are somehow, I mean, the way to think about it is that if you, if you, for instance, take the, if you take the torus, then you can take the handle body inside, but then also the handle body outside as complement in the 3-sphere. Both of these handle body groups that generate the mapping class group. So you have already both, and the question is, when does it descend to the mapping class group of the surface? Generally it won't, but you, so you will, when you want to write a mapping class group element of the surface as a word in mapping class group elements for the inside and the outside handle body, then there will be some ambiguity, and what basically this whole thing does with the factorization homology is to somehow show that this ambiguity just consists in a central element. This is basically also what this is basically the Skane theoretic approach to these mapping class group representations that Marsbaum and Roberts also use. Yeah, so you show that somehow the ambiguity that you get from these handle body groups a priori just consists in a scalar, and then you will still get a projective representation. This is something that I omitted in this talk, that the representations that they're just projective, but yeah.
Are there more questions?
Yeah.
So for this result, where you have this space is either contractible or empty, you have a characterization of when it's empty.
It's empty when you don't have that. The connectedness is exactly the situation in which somehow it's contractible. So it's relatively difficult to we haven't seen interesting cases where it's empty. I think if you have so my guess would be that if you have a finite ribbon category with a very degenerate braiding, in the sense that if it's symmetric, then maybe you don't have problems, but if it's not really symmetric but still has a large Muga center, so a lot of objects that trivially double braid, then my guess would be that you don't have that, and then here you would be in a situation where it's empty. But that's a good question, actually. It's not so. So far, we concentrated on the cases where it actually works, because the purpose was to actually construct the modular functors and understand the existing ones better. But yeah.